All we're going to cover in Chapter 11 is the first three sections. And what we're going to be talking about is analysis of categorical data. We're talking about data that can be separated into different categories, sometimes in a table, sometimes just in a column. And when we do hypothesis tests with this kind of data, we're going to be looking at the observed frequencies and whether they agree with a set of expected frequencies, so whether they conform to some specific distribution or not. One of the things that we'll be looking at is contingency tables. These can also be called two-way frequency tables. This is a table that has at least 2 rows and at least 2 columns. And for all of the hypothesis tests in this chapter, we'll be using a different distribution. We haven't used this one before. It's called the chi-square distribution. And it's a little bit different than either the normal distribution or the t-distribution. We'll take a little bit of time here and look at what it looks like. Some of the properties of the chi-square distribution. First of all of the values of chi-squared are non-negative. So they're either 0 or positive. And this distribution is not symmetric. So like I said, it's a little bit different than what we're used to dealing with. This is another type of distribution where we'll need to know the degrees of freedom, because the distribution looks a little bit different for each different value of the degrees of freedom. And here's a picture of what the distribution can look like. Notice over here we said it's not symmetric. It is going to have a kind of a hump, but it's not necessarily going to be in the middle. And notice also here that the distribution starts at 0 and only has positive values for chi-squared. And here's what the distribution looks like for 2 different degrees of freedom. This one in the blue is for 10 degrees of freedom, and notice it's got a higher hump and it's a little bit steeper and it goes down quicker on the right end. If we have 20 degrees of freedom, the hump isn't so high, it comes up a little bit more slowly and goes down a little bit more slowly. There's a table for the chi-square distribution in the back of your book, or also available on Course Compass. And one of the different things with the chi-square distribution is that the table gives you cumulative areas from the right. Remember when we talked about the normal distribution, using the table for that gave you areas coming from the left. The chi-square distribution is exactly the opposite. You get areas coming from the right. And the way that you find your critical values with the chi-square distribution are that you find degrees of freedom, that tells you what row to look in, and then you use your significance level alpha to figure out which column to look in. And the only kinds of hypothesis tests we'll be doing in this chapter are right-tailed tests. So that's the only thing that we're going to talk about finding critical values for. Here's an example. We're going to find the critical value for a right-tailed test with alpha equal to 0.05 and 13 degrees of freedom. So here's what our table looks like. Now, since we know we have a right-tailed test, all we have to look for is alpha in our columns. So here's the column that has the 0.05, which was our alpha. So that's the column we're going to look in, and then we said we had 13 degrees of freedom. So we're going to be looking in this row. And that gives us a critical value of 22.362. Okay, we're ready to talk about the first type of hypothesis test, which is a test of goodness of fit. For this type of test, we'll have a single row or a single column of values. This is basically going to be a frequency distribution. So we'll have different categories and frequencies for each category. The hypothesis test will be to see whether those observed frequencies fit with some specific distribution. And when we look at the formulas for the test statistic, there's some notation that you need to know. A capital O is going to represent an observed frequency. A capital E will represent an expected frequency. K, this is an important one, this represents the number of different categories or outcomes. And that will have to do with your degrees of freedom, so that's one that you do need to know. And N will represent the sample size or the total number of trials. And the requirements to do a goodness of fit test, we have to have randomly selected data, and the sample data has to have frequency counts for each of the different categories. And for each category, the expected frequency has to be at least 5. And notice that this is the expected frequency, not the observed frequency. And here's the actual formula for the test statistic. This isn't something that we're actually going to use because we're going to use technology to calculate our test statistic for us. But if we were going to use it, what happens here is that the capital O is the observed frequency for a specific category. The capital E here and on the bottom is the expected frequency for that same category. So the difference between the observed and the expected gets squared, and then it's divided by the expected frequency. What that means is that the bigger the difference between the observed and the expected frequency, the more that contributes to the total value of your test statistic. So the more differences there are between the observed and the expected frequencies, the bigger your test statistic is going to be. And we already looked at the chi-squared table to talk about how to find critical values. The important thing here is that when we're doing a goodness of fit test, the number of degrees of freedom we have is k minus 1, where k is the number of categories we have. So for example, if we have a distribution with 5 categories, then our degrees of freedom would be 4. And goodness of fit hypothesis tests are always going to be right-tailed tests. Now we can have two different situations. Sometimes the distribution that we're trying to fit to is where all of the expected frequencies are equal. So to find the expected frequency for each category in that case, we would just take the total number of trials and divide by the number of categories. So n is going to be the number of trials or the sample size, and k is the number of categories. Now we can also have distributions where the expected frequencies aren't all equal, and in that case we'll have a proportion for each category, and that's the distribution that we're trying to fit to, and then we'll have our n, which is still our sample size or our number of trials. So the expected frequency for one particular category is going to be that number of trials times the proportion for that category. And as I said a little while ago, if our observed and expected frequencies are close together, then we'll end up with a small value of chi-squared, our test statistic. That will give us a large p-value. If we have a large difference between the observed and expected values, then we'll get a large value of chi-squared and a small p-value. And if our value of chi-squared is large enough, then our conclusion will be to reject the null hypothesis, and that will mean that there's support for the claim that the values don't fit with the distribution. So here's a little diagram that gives you an idea of the two situations that we can have. So what we're doing again is comparing the observed frequencies and the expected frequencies. If these two are close together, then we end up with a small value of our test statistic and a large p-value. So if right here is our critical value, then if our chi-squared value is small, it will be over here, which would not be in our rejection region, because our rejection region is going to be over here in the shaded area. So if the chi-squared value is small, if it's smaller than our critical value, then our conclusion would be that we'd fail to reject the null hypothesis, and that means that we do have a good fit with our claimed distribution. Now on the other hand, over here, if our observed and expected frequencies are far apart, then we end up with a large value of chi-squared, which is going to put it in the rejection region. That means that our initial conclusion would be to reject the null hypothesis, and that means that we don't have a good fit with our assumed distribution. Here's an example. There are some data sets in the book that include health information from a random sample of 40 males and another random sample of 40 females. Now when you get weights of people, it's very important to actually weigh them instead of just asking them their weight, because most people tend to round off their weights to the nearest pound, or even to the nearest 5 pounds, or even to the nearest 10 pounds. So by looking at the last digits of the weights that are in those data sets, we can get an idea whether the weights were obtained through actual measurements or whether the subjects just reported their own weights. So what we're saying is that if the weights were actually measured, then the last digits of the weights should have a uniform distribution. In other words, there should be about as many zeros as there are twos, as there are sevens, and so on. So what we're going to do is test the claim that the sample is from a population of weights where the last digits don't occur with the same frequency. If that's the case, then we would think that maybe the weights were reported instead of actually being measured. So here's our data. This is data from 80 subjects, so that means our N is equal to 80. And here are our frequencies. So there were 7 of the weights that had a last digit of 0, 10 that had a last digit of 3, and so on. Now, one of the nice things about a test for goodness of fit is that the null hypothesis and the alternative hypothesis are always pretty much the same. Since we're testing whether the categories are equally distributed, that means that our proportion for each category is going to be the same. And since we have 10 different categories, that means that each one should have a proportion of 1/10. So our null hypothesis is that the proportion for each of the 10 categories for each of the 10 digits is 1/10 or 0.10. Our alternative hypothesis is just the opposite of that, which would say that at least one of these proportions is not 0.10. And the problem gave us our alpha of 0.05. Now we're going to look at how to use StatCrunch to do this. What we need for StatCrunch is not only our observed frequencies, which we already have, but we also need our expected frequencies. And we have to put both of these into StatCrunch. So that's what I've done here. I typed in all of the observed frequencies that we already had. And then remember, in this case, we're assuming that these are equally distributed. And we said that there were 80 values. And the distribution that we're trying to fit this to is that each of the proportions is 1/10 for each category. So that means our expected frequency for each category, remember this was N times P, so we're going to have 80 times 1/10 for each one, and that gives us 8 as an expected frequency for each category. So what we would do is just type these two sets of values into StatCrunch in 2 columns. I went ahead and named these columns observed and expected so that I would remember which one was which. Now if we do a goodness of fit test with StatCrunch, then here are the results that we get. And notice it tells you which columns you picked for the observed and which you picked for the expected, just in case they're named something differently. It gives you your sample size, your degrees of freedom, and remember that was the number of categories minus 1. So we had 10 categories, that gives us 9 degrees of freedom. Where it says chi-squared, that's your test statistic. And it also gives you the p-value, in this case, which is 0.259. Now we could also do this using a critical value. So we have our test statistic here of 11.25. We know our degrees of freedom was 9 and our alpha was 0.05. So for our critical value, we'd look in the 0.05 column and the row with 9 degrees of freedom, and that would give us a critical value of 16.919. So for using that critical value, we would graph it on our chi-squared distribution picture. So there's our critical value. Our test statistic was 11.250, which would be over here somewhere. So it is not in our rejection region. Our rejection region is over here. So that would tell us that we would fail to reject the null hypothesis. The other way we could tell this is because our p-value was 0.259. Our alpha was 0.05, and that means the p-value is greater than alpha. And that also tells us that our initial conclusion is that we failed to reject the null hypothesis. So our final conclusion is that there's not sufficient evidence to support the claim that the last digits do not occur with the same relative frequency. This is saying there's not enough evidence to support the claim that our observed values don't fit the claim distribution. So this was our claim. We didn't find enough evidence to support that. Which means we're actually saying that the last digits are a good fit for our claim distribution, which was that all the categories are equal. And that means that the weights were probably actually measured instead of being reported. Okay, the next test we're going to talk about is a test of independence. And this is where we have a table with at least 2 rows and at least 2 columns. We call this a contingency table. And what we're going to look at is whether the variables that make up the rows in the table are independent of the variables that make up the columns in the table. In other words, whether the 2 variables are related to each other or not. And here are the requirements for doing a test of independence. Again, we have to have randomly selected sample data. It has to be represented as frequency counts in a 2-way table, and sometimes you have to actually create the contingency table. And for each cell in the contingency table, the expected frequency again has to be at least 5. That doesn't mean that your observed frequencies have to be at least 5. And just like for our goodness of fit test, for the independence test, the null and the alternative hypotheses are always the same. The null hypothesis is always that the row and column variables are independent. The alternative hypothesis is always that the row and column variables are dependent, or in other words, that they're related to each other. And here's our test statistic. This looks just like the one that we saw for the goodness of fit test. And in fact, it's very similar, except this one is actually even a little bit worse to try to calculate by hand because you just end up having more values. But again, the O stands for observed frequencies, the E stands for expected frequencies. And again, the more difference there is between the observed frequencies and the expected frequencies, then the bigger test statistic you're going to get. And you can actually calculate that test statistic by hand, but we're not going to do that. We're going to let our technology do it for us. That's what we use to calculate our degrees of freedom. So you take your number of rows minus 1, your number of columns minus 1, and you multiply those 2 numbers together, and that gives you your degrees of freedom. And tests of independence are always going to be right-tailed. Now what we're doing with this test of independence is just seeing if there's a relationship between the 2 variables. That doesn't mean that there's a cause and effect link. So it doesn't mean that a change in one variable causes a change in the other variable. Here's an example. A lot of people use echinacea to try and treat colds. So there was a study done on this. Some test subjects were treated with echinacea in a 20% ethanol solution, some were treated with echinacea in a 60% ethanol solution, and others were given a placebo. All of the test subjects were exposed to the rhinovirus, which is the common cold, and then we have results about whether each of the test subjects became infected with a cold or not. So what we want to know is the infection or no infection related in any way to what treatment group the subject was in. So the requirements for the test of independence, we have to have randomly selected samples. So the subject were randomly assigned to the different treatment groups. And our expected frequencies have to all be at least 5. Now our null hypothesis is that the row and column variables are independent. Our row variables are whether the subject's got an infection or not. Our column variables are the treatment group. So we're looking at whether those 2 things are independent or not. Our alternative hypothesis is that they're dependent, in other words, that they're related to each other. Now here's how we use StatCrunch for this. If you have summary data like we do, which is already in a table, then you just type it in and make your own table in StatCrunch. And I would suggest that you use column headers so that you know which column is which in this. You also have to put in another column that gives your values you have for your row variable. So here are all the numbers from the column, and then in this case I just put the row labels in the 4th column over here. But I could have put them in the first one on the left too, it doesn't really matter. Then you go to Stat Tables Contingency, and since this time we had summary data, we would do with summary. And then you just select the columns that you had for your column variables. And remember for this, you can't select the one that you had your row labels in. So we want these 3 for our column variables, and then our row labels were in the column called variable 5. And you can also, with this, you can have StatCrunch tell you different percentages if you want. So you can get a row percent, a column percent, a percent of total, or an expected count, which is like an expected frequency for all of the cells, if that's what you want. When I did this example, I didn't select any of those. But here are the results. We've got our contingency table printed back out. Notice it put column and row totals in for us. And our statistic is chi-squared. Our degrees of freedom is 2 because we had 2 rows and 3 columns. So we end up with 2 minus 1 times 3 minus 1, which gives us 2. Under value right here, that is the value of our test statistic. And our p-value is 0.2316. And if we look at our chi-squared table to find our critical value, we would find out that our critical value is 5.991. So here's the picture of our distribution. Here's our critical value, and our test statistic would be over here. And again, that's not in the rejection region. So whether we're thinking about the critical value method or the p-value method, either way we would get the same conclusion. Because if we compare our p-value to our p-value is going to be greater than alpha. So that way we get the same conclusion that we're failing to reject the null hypothesis. That means that there's not enough evidence to support the claim that the echinacea treatment and the infection are dependent or related, which means that they're independent, and that means that echinacea is not making a difference in whether the people get an infection or not. Now here again we have a diagram about what happens with your test statistic and your conclusion. So if the observed and the expected are close together, then you get a small chi-squared value, which means it will end up not in the rejection region. Then your conclusion is that you fail to reject the null hypothesis, which was independence. If your observed and expected frequencies are far apart, then you get a large value of chi-squared, which is going to put it in the rejection region. And that means you'll end up rejecting the null hypothesis, so rejecting the claim of independence. Here's another example. In this one we had a treatment for headaches. So we had the treatment drug and a placebo, and then we had data about whether the subjects had headaches or didn't have headaches. So here's the contingency table, and here are our results. And notice that in this one we only have 2 rows and 2 columns. So our degrees of freedom would be 2 minus 1 times 2 minus 1. So our degrees of freedom just turns out to be 1. Our test statistic is 1.798, and our p-value is 0.1799. This is a fairly large p-value. If we're testing this at a 0.05 significance level, this is going to be greater than our alpha, which was 0.05. And that means that our conclusion is that we fail to reject the null hypothesis. And that again says that our row and our column variables are independent. In other words, the drug wasn't making a significant difference in whether the subjects had headaches or not. Here's one more example. In this one, we're going to test at a 0.10 significance level. In this case, subjects were given a survey. They could answer yes, no, or undecided, and then it was determined whether the subjects were employed or unemployed. So the question is whether their answer to the survey question was related to their employment status. And here are the results from StatCrunch. We had degrees of freedom of 2 since we have 2 rows and 3 columns. Our test statistic was 5.942, and our p-value is 0.0513. Now remember, in this one our significance level was 0.10, so we actually have a p-value that's smaller than our significance level. And that means our conclusion, our initial conclusion, would be to reject the null hypothesis. That means that we're rejecting the claim of independence, which means that there is a significant relationship between the employment status and the answers to the survey question.